In this example, we are given an in situ value for a moist soil with a total volume of 0.3 meters, a total weight of 5,500 newtons, and an oven dry weight of 4,911 newtons, and then a specific gravity of 2.74. And we're being asked to compute the moisture content, the total unit weight, the dry unit weight, the void ratio, porosity, and degree of saturation. So first, again, this is actually example 3.2 in the textbook, but I do want you to fully absorb how we solve this in this video. We are not going to solve this problem the same way example 3.2 solves it. I am not a big fan of how the textbook solves some of these problems. So we are going to do what we've been talking about. We're going to fully populate a phase diagram, and then we're going to use the basic definitions of the ratios to solve for our desired quantities. The first thing I do want to mention is the word in situ. In situ means basically from the ground, from the soil. So when we say in situ, we mean that this soil sample was directly pulled right out of the ground, and it was moist, and 0.3 cubic meters was pulled out of the ground directly, and the total weight was 5,500 newtons directly out of the ground. So kind of remember what that term means, in situ, because you're going to see it quite a bit in this course and future courses. The next thing we want to point out is that we're given weights. So we're going to be dealing with unit weight this time, not density, okay? So let's go ahead and get started. Under solution, we're going to begin by drawing the phase diagram. Draw the phase diagram. Okay, and again, we're going to always begin our problems with drawing the phase diagram. So here we go. We have air, water, and soil solids, and I'm going to put the weight side on the left, and it's going to have units of newtons, and then on the right, I'm going to have the volume side with cubic meters, okay? So on the weight side, of course, the weight of air is negligible, so we're going to have a weight of water and a weight of soil solids, and then, of course, we have the total weight here. Now, remember, we were given a total weight, right? We were directly told the total weight is equal to 5,500 newtons. And then we were also given a weight of soil solids of 4,911 newtons. So there we go. And then on the right side, of course, we've got volume of air, volume of water, volume of soil solids. The air and water volume together make up the volume of voids, and we do have a total volume, and we were given the total volume, right? We were given the total volume is equal to 0.3 cubic meters, okay? So my first question, before we really get into all the calculations, do we need to assume any values are equal to 1? And the answer is no. We're going to say no need to assume any values equal 1, since we know at least one non-ratio value. In fact, here we know 3 of them. We were given 3 non-ratio values: total weight, weight of solids, and total volume. So let's go ahead and get started in populating this. Well, the first thing we can easily calculate is the weight of water. Just look at the weight side of that phase diagram. The weight of water should just be equal to the total weight minus the weight of soil solids, right? So if we say 5,500 minus 49, 55, type that in my calculator wrong, 5,500 minus 4911, we should clearly get 589 newtons as my weight, as our weight of water. So we're going to populate that in here, 589, okay? What next? Well, this problem actually is not too complicated to get these other values. How do we relate weight and volume? Well, we relate them by unit weight. So we can make a note of that. We can say relate weight and volume by unit weight. Okay, so where do we want to start? Well, we can deal with water first if we want, right? We can relate the weight of water to the volume of water because we know the density of water, right? So let's start with that. How about that? So we're going to say not density, unit weight of water. I'm sorry. We're going to say unit weight of water is equal to the weight of water divided by the volume of water. And we can do some rearranging, and we say the volume of water equals the weight of water divided by the unit weight of water. What is our weight of water? Well, we just figured that out. It's 589 newtons. And what's the unit weight of water? It's not 1. It's not 1,000. It's 9.81 kilonewtons per meter cubed, or 9810 newtons per meter cubed. Okay, so 9.81 kilonewtons per meter cubed, or 9,810 newtons per meter cubed. So we can solve for the volume of water as the following: 589 divided by 9810. And we should get a volume of water of 0.06 cubic meters, and we can populate that part of our phase diagram right now, 0.06. Okay, now we're going to do something similar but with a volume of solids. Now, were we given a density of soil solids? Not really, but we were given a specific gravity of soil solids. So let's use that now. So let's say the specific gravity of soil solids is the unit weight of soil solids divided by the unit weight of water, okay? Basic definition of specific gravity. And then we're going to say the unit weight of soil solids is the weight of soil solids divided by the volume of soil solids. And then our unit weight of water is still down there in that denominator. So what are we really looking for? We're looking for this value right here, the volume of soil solids. So if I kind of repackage this just a little bit, we get W sub S over gamma water times V sub S. And then we can rearrange this and we'll get the volume of solids. Soil solids is equal to the weight of soil solids divided by the unit weight of water times G sub S. Do we have all three of these values? Absolutely. So the weight of soil solids was one of our given values, 4,911 newtons. And then we divide by 9810 newtons per meter cubed. And then in that denominator, we also put 2.74, which was the specific gravity value of soil solids that we were also given in the original problem statement. So 4911 divided by 9810 times 2.74. Watch your calculator punching, but I get 0.183 cubic meters as my volume of soil solids. So I can populate that here, 0.183. Now, I think I mentioned this in class. When you're populating these values, you need to take these values to 3 or 4 sig figs. If you round them off to 1 or 2 sig figs, then you're going to introduce some error in there. So I would take all these values to 3 or 4 sig figs as you're doing these calcs, okay? So what do we have left to calculate for this phase diagram? We got volume of air and volume of voids. So can we calculate these pretty easily? Yeah, absolutely. So the volume of air is going to be the total volume minus the quantity of the volume of water plus the volume of solids. So we're going to have 0.3 cubic meters minus our volume of water, which was 0.06 cubic meters, and then also distribute that negative, minus 0.183 cubic meters. So my volume of air is calculated as 0.3 minus 0.06. So I get 0.0573 cubic meters as my volume of air. Okay. 0.0573. And then my volume of voids, of course, is just the volume of air and volume of water added together. So we can easily compute that as 0.117. Okay. Now, just to be, kind of proper and show my work, I'm just going to go ahead and write that out. Volume of voids equals volume of water plus volume of air, just to, make it known that I know where that came from and I'm showing my work. Okay. So now our phase diagram is fully populated. We know all of the individual values we need. So now we're ready to calculate all of the ratios, okay? So let's go ahead and get started with that now. We can say the moisture content is the weight of water over the weight of soil solids. So that would be 589 newtons divided by 4911 newtons. So 589 divided by 4911, and we get 0.12, or if you like a percentage, you can say 12% moisture content, all right? We want the total unit weight. That's going to be total weight divided by total volume. So that would be 5,500 divided by 0.3, and I get 18,333 newtons per meter cubed, or more conveniently 18.3 kilonewtons per meter cubed. Now I do want to remind you, is a kilonewton per meter cubed a kilopascal? And the answer is absolutely not, okay? A kilopascal is a kilonewton per meter squared, which is a stress value. This is not stress, this is unit weight. So you cannot say kilopascal here. You keep it as kilonewton per meter cubed, okay? Let's keep moving on. We're gonna say the dry unit weight is the weight of soil solids divided by the total volume. So my weight of soil solids was also given to me as 4911 newtons divided by the total volume is 0.3 cubic meters. And we say 4911 divided by 0.3. And converting to terms of kilonewtons, I get 16.37 kilonewtons per meter cubed, okay? And then my void ratio, volume of voids divided by volume of solids. So let's see what those two numbers are. Volume of voids was 0.117. Volume of solids is 0.183. So what does that come out to be? I get 0.64 as my void ratio, 0.64. My porosity is volume of voids over total volume, okay? So that's 0.117 divided by 0.3. So I get a value of 0.39 for my porosity. And then finally, our degree of saturation as a percentage, the problem did ask for it as a percentage, is volume of water over volume of voids. So looking back at our phase diagram, our volume of water was 0.06 cubic meters. Volume of voids is 0.117. So 0.06 divided by 0.117. And as a percentage, you want to multiply that by 100. So let's write that in there times 100. And I get 51.2%. And that is it. So again, in summary, we fully populated the phase diagram, right? Fully populated the phase diagram, and we related weight and volume by unit weight terms. And then we use the basic ratio definitions to calculate all of the values we were looking for. We did not use any of those derived formulas to do this. We used just the basic ratio definitions, okay? We also did not need to assume anything was equal to 1 at the beginning of the problem because we were given at least one value to start with that was a non-ratio value, okay? So that's why we didn't need to assume anything was equal to 1. Now, I'm going to make a comment based on a question we got in class before. So when you are given values that's a non-ratio form, like a total weight or a total volume, in this case we had both of those, then we have a physical soil sample here with us. We could have this physical hunk of soil sitting right in front of us, okay? So when we're given values that are non-ratio values, these calculated values that we populated our phase diagram with are actual hard numbers. These numbers are not going to change. These are actual physical numbers, okay, of a soil sample that we have. All right, maybe it came out of a Shelby tube. Maybe it came out of a split spoon. Either way, these are actual numbers of a real soil sample we have. Now, if we had a problem where we did have to assume something was equal to 1, in that case, some of these values we don't know them for sure. We don't know any of them as hard values because we had to assume something was equal to 1. So that's kind of the difference between when you're not given any values that are an individual value, that's a non-ratio, versus when you are given values that is a single value in non-ratio form like we were given here. So make sure you're thinking about that as you're solving these problems.